This video goes with page 131 and 132, so I want you to kind of do this with me as I go here. So the first thing that I want you to do is I want you to draw the Lewis structures for the first 1, 2, 3, 4, 5. Let's see, for the first 5 elements, go ahead and draw the Lewis structures. You can pause the video now, or you can just watch it and do it with me, but I want you to make sure that you know how to draw these. Okay, now the first one is BEF2. Now, beryllium beryllium violates the octet rule. So beryllium only has 2 valence electrons, and so fluorine has 7. So if you count these up, 14, 15, 16, your picture has to show 16 electrons. So you'll put beryllium Be in the middle, and you'll go F on the outside, F on the outside, and then you got to complete the octet for the fluorines, and then you can count 6, 12, 14, 16. Okay, that's 16. That's all the electrons you have. Beryllium never gets any lone pairs on it like that, so beryllium violates the octet rule. Okay, carbon has 4 valence electrons. Oxygen has 6, plus 2 is 12. So 12 plus 4, that's 16 that your picture has to show. So put carbon in the middle, put oxygen on the ends. And anyway, you can start adding the electrons. And what you will notice is that you have to double bond both carbons. So it should look like that. All right. Okay, O3, that has 18 valence electrons. Oh, I guess I should count 2, 4, 6, 8, 10, 12, 14, 16. Okay, O3. So you connect oxygen with a single bond. This is how I do one. I guess if you watch my other videos, you would know. I usually put 8 around everything to start with, unless I know it violates the octet rule, which this one doesn't. But then if you were to count this, you would get 6, 12, 14, 16, 18, 20. You would see that you would be 2 over what you need. So, because 20 minus 18 is 2, so you're showing 2 extra. That means you need to add one more bond. And so you could add one more bond. But when you add that bond, you have to erase lone pairs in order to satisfy the octet rule. Now that's how I draw Lewis structures. And so that's the correct structure for H2O or CO2. My bad. All right. Now H2O, you should probably know how to draw that, but it's H, O, H, and then lone pair. Now I like to draw like that. And then let's see, SO2. Okay, so S, O, and O. Oops. Pen's going crazy here. Excuse me. Okay, there would be a double bond here. It'd be just like O3. All right. All right. Anyway, and I gotta have one lone pair on the top there. Okay, so now here's what all these 3 have in common. Okay, all these have in common. The reason I wanted you to draw the first 5 here, they're all like 3 atom compounds. And as long as they don't have an expanded octet, like we'll do some later that are expanded, but the non-expanded octets, that means nothing violates, like goes over 8 on the central atom. Okay, 3 atoms can either be, so like a 3 atom molecule, so 3 atom molecule can either be linear or bent. So the geometries are either linear or bent. So what you got to do to figure this out is you want to look at the central atom. So look at the central atom. If there's no lone pairs on the central atom, then that is linear, because according to VS EPR theory, which is called valence shell electron pair repulsion theory, these electrons right here that I'm pointing in red want to be as far apart from these electrons right here, and that angle would then be 180 degrees. And so that makes it linear. Okay, let's look at CO2. All right, so you find these electrons right here. They want to be as far from these electrons right here. So what would that angle be? That's going to be 180 degrees. And so that also is linear. Okay, now let's look at, so what we're basically looking at is we're looking at the electron domains around the central atom. Okay, so like if we were to look at the domains around O3, there's one domain. Double bonds count as one domain. The lone pair counts as a domain, and this lone pair counts as a domain. So you have three electron pairs or three electron domains that really want to be as far apart from each other as possible. So when you have three things that want to be as far apart as possible, okay, that ends up being what's going to be called a bent geometry. It's going to be bent, but you should probably know the angle. Like if you have like a circle with three things as far apart as possible, that's bent, and it's called bent 120 degrees, because if you take a circle and divide it into three parts, it's 120 degrees, okay? Now, here's another one, okay? Here's four, this one has four electron domains, 1, 2, 3, 4, okay? So in water, okay, you have four electron domains around the central oxygen. Okay, that also is going to be a bent geometry, but the bent geometry, when you have four domains, it's approximately 109.5 degrees. Okay, but technically some people have done their research on this and it's not exactly 109.5, but if you say it's around 109.5, you would be close enough, okay? So here's kind of the thing. Whenever you have three atoms, always look at the middle atom. If the middle atom has no lone pairs on it, it's linear. If the middle atom has a lone pair on it or two lone pairs, it's bent. Okay? So they're either linear or bent. Okay, why don't you look at SO2? Let's see how many domains that it has. Okay, so it has 1, 2, 3. So do you think that would be linear or bent? Okay, well, three domains around the middle, it's going to be bent. And the approximate angle, when you have three things, that's going to be 120 degrees. Okay? We're going to do bond angles later, but that's something you should start working on. Okay, now let's draw the next three are all 4-atom molecules with a non-expanded octet. Okay, so boron has 3, fluorine has 7 valence, so 7 times 3 is 21, plus 3 is 24. Our picture has to show 24, so we go B, F, F. Now, boron is also a violator of the octet. That's supposed to be 1 electron there. Boron's also a violator of the octet rule. So it doesn't get a lone pair on it because it only has 3 valence electrons. So 18, 20, 22, 24. So you see boron, if you look at the dot structure of boron, it only has 3 valence, so it's not going to have a lone pair on it, okay? So they go with the fluorine, and that gives you 24. Boron is another violator of the octet rule. Okay, NO3. So we could draw this, and if you remember, nitrogen, or the nitrate, has a double bond on one of them. And anyway, it kind of looks like this in brackets. It's an ion like that. Okay, and NH3. All right. Okay, NH3 would look like that. Now, when you look at these 4 atoms, okay, the 4 atom molecules, Okay, with a non-expanded, because with expanded, then things can go different here. But non-expanded, that means that the middle atom doesn't have more than 8 around it. Okay, whenever you have 4 atoms, they can either be trigonal planar or trigonal pyramidal. The key to figuring out which one's which is to look for a lone pair on the middle atom. So if we look at BF3, look at the middle atom only. There's only 3 domains. And so because there's only 1, 2, 3 domains on the middle atom, that's trigonal planar. And the bond angle is 120 degrees. Okay, let's look at NO3. You count the domains on the middle atom. 1, 2, 3 electron domains. 3 electron domains, still trigonal planar, and it's 120 degrees. Now let's look at NH3. 1, 2, 3, 4 domains, okay? You see the difference between, these 3 are all 4 atom molecules, but this one has 4 domains. These only have 3. So when you get 4 atom molecules with 4 domains, it's not called trigonal planar anymore. It's called trigonal pyramidal. Okay, and then the bond angle, what's the 4 domain bond angle? Well, you would just look up here. You have to memorize this number, but a 4 domain bond angle is 109.5. That's a number that you should memorize, 109.5 degrees. Okay, well, we have one more to do here, and that's CH4. You've probably drawn this one a million times. All right, so anyway, C, H, 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 H. Remember, you could add up the valence here. 6 plus 4, that's equal to, or no, 4, because carbon only has 4. 4 plus 4, that's 8. 2, 4, 6, 8. So that's what we have here. Okay, whenever you have a 5 atom molecule and it's a non-expanded octet, that means there's not more than 8 on the middle one. Okay, that shape, you have to memorize this shape. It's called tetrahedral. Okay, and so basically that's your 5 atom molecule non-expanded octet, tetrahedral. Okay, now we're going to do some other ones with 5 atoms, but they're expanded. That means that it has more than 8 around the middle. Those are not going to be tetrahedral. Now the bond angle, you just count the domains again. There's 1, 2, 3, 4 domains. A 4 domain bond angle is 109.5 degrees. Okay? All right, that's it for this video. So there'll be another video that goes with this, going over the shapes again in a minute here that you can look at.